Hello everyone. Today I will be talking about a recent work that I've been doing on future projections for elusive dark sectors. This is a work in progress that I've been doing with my collaborators here, Rashmish Mishra and Marco Costa. I like to think of what we're doing as a way to save the taxpayers' money by actually looking for a model-independent way to constrain new physics. So sometimes we tend to feel stuff that we don't actually see. As we all know that there is much more stuff out there in the universe that exerts gravity on us than we actually see. This is the stuff that we call dark matter. Now, over the years, much evidence has piled up, however indirect, in favor of this dark matter. This dark matter can flatten out galaxy rotational curves, it can twist light and give us gravitational lensing, and much more. Now, it is highly plausible that nature has a dark sector that contains the dark matter. Now, this sector is dark because it does not contain any quantum number under the standard model. It is likely, though, that this sector could be talking to the standard model via some portals. Now, a portal interaction can be written as a product of a dark sector singlet operator and a standard model singlet operator. Now today I will be talking about the case in which the dimension of these portals is greater than 4, or the so-called irrelevant portals. There's a vast literature that exists for the case in which the dimension of these portals is less than 4. So I will stop talking about that now. Now, in the case of dark sector, which interacts with the standard model via irrelevant portals, there's a really weak coupling, and hence they become the really elusive dark sector. Now, in order to derive bounds in a model-independent way, we have a couple of minimal assumptions that are in place. We characterize the dark sectors based on two energy scales, the lambda UV scale, which is the scale at which the mediators are exchanged, and the lambda IR scale, which is the scale at which the lightest state lives. Now, there is a large hierarchy between these two scales, and hence at energies which are very far away from these two scales, we know that the theory is going to be approximately conformal. Now, these conformal dynamics let us calculate the rates and cross-sections in a model-independent way. Now, benchmark models that lie in this scenario include pure Yang-Mills dark sector, which contains the glue ball dark matter, free fermion dark sector, and as well as the 5D Randall-Sundrum models. So let's talk about how we would produce this dark sector at colliders. Here's a cartoon showing just that. Let's collide two protons inside the detector. And in this way, we would produce a lot of standard model particles. Let's say we produce the Higgs. Now, this Higgs would produce dark sector via some portal. The cross-section for the production of this dark sector would be inversely proportional to lambda UV squared raised to d minus 4 power, where d is the overall dimension of the portal. And then we have this crazy dark sector world where we have crazy dark showers and really fast inter-ds decays. Now, eventually all the dark sector stuff would decay to the lightest dark sector particle, shown here as LDSP or the LDSP. Now, this LDSP would travel a bit before decaying back to the standard model via portals. The lifetime for this LDSP would depend on the ratio of the two scales. Now, depending on how long the lifetime is, we can have different kinds of signatures. So if the LDSP escapes the detector because it has a really long lifetime, we have missing energy. In the case that the LDSP decays inside the detector, we have displaced vertex. So in that case, we would expect to see charge tracks and jets from the standard model as a signature. Now we ask ourselves the question, how can we use these signatures that I just talked about to constrain this scenario of dark sectors. Now in this parameter space where I have the UV scale on the y-axis and the infrared scale on the x-axis, I would expect missing energy searches to pop up like these plateaus. So this colored region is basically the area that is excluded from some searches. So they could be current or future searches. So future searches are always projections. Displaced vertex searches are going to pop up like hump. So this is just schematic. It's not really, I wouldn't expect a triangle. So yes, displaced vertex searches are going to pop up like these humps. There is going to be upper bound on the lifetime of the LDSPs, which comes from the Big Bang nucleosynthesis. We would want the dark sector particle to decay before the BBN gets over, so which is before 1 second in cosmological history. Finally, we have prompt decay searches, which is basically model dependent. So we will not be talking about this. Now here you see constraints that are coming from the two signatures that I just talked about, taken from this very recent article by Contino, Max and Mishra. Now on the y-axis here I have the lambda UV scale, and on the x-axis I have the ratio between the two scales. In this plot they're fixing the production portal to the Higgs portal, so we have OHH. The humps are showing the parameter space that is excluded by current displaced vertex searches, so mainly this Atlas search, which is a recent search for displaced vertex. And the slabs are exclusion plots coming from the missing energy searches. So depending on the color, we can have various decay portals. Decay portals are the ways in which the LDSP is decaying back to the standard model. So it could be via OHH portal or JJ or else TT. So we asked ourselves the most obvious question, what could we do to improve our reach on lower lambda IR? So could we start filling up this white space in the future, especially with all these proposed experiments? Now I'm going to take a slight detour and explain the huge zoo that has been proposed for detecting long-lived particles in the recent past. So there are all these experiments that have been proposed, from Methuselah, Codex B, Anubis to Alex. The main idea behind these detectors is that they comprise a box or a decay volume that is close to some LHC interaction point. Now this basically allows the long-lived particle, or in our case the LDSP, to decay. Now depending on the size, we can have something like a 200-meter huge Methuselah, or else we can have something very compact like Codex P, which has the dimensions shown here, 10 meter cross 10 meter cross 10 meter. Certain experiments that have been proposed also make use of some pre-existing cavity close to the interaction point. So there's Anubis, and Alex does the same, that it would replace Alice. So here I am showing a very preliminary plot showing all the space that is probed by the future experiments. Now here I am fixing the production portal to OHH, which is the Higgs portal, as before. I am only concentrating on the signatures in the form of these humps coming from displaced vertex searches. Now the decay of the LDSP back to the standard model is taking place through the JJ portal in this, where J, mu, nu, Sm can be given by these two operators. Now we can see the various future projections that the experiments that I just talked about are going to have. So this is all the area that is going to be excluded eventually. Now you can see in this blue circle the current Atlas search. So this gives us a comparison with what we're going to have in the future. So we can see that we can eventually start, probing this white space that I just talked about earlier. So this brings me to the conclusion. We saw how dark sectors that are talking to the standard model via irrelevant portals are very elusive. We saw that current experiments are leaving, in fact, a lot of parameter space untouched for these elusive dark sectors. We saw that future experiments dedicated are going to be very powerful probes for such elusive dark sectors. Now, the next thing we want to look at is we want to see how our model independent bounds are going to actually look when superimposed on a particular model. And let us know if you have some model in mind or some experiment. We'd be very happy to chat. Thanks a lot.